Okay, hello, I'm Ethan Ko. My topic is extended Kalman filter localization, and I'm currently presenting from home. I chose this topic because I'm very interested in robotics, and EKFs are a very powerful way to estimate a robot state. For my project, I created a Python simulation of a Mechnum wheel robot and implemented an EKF on it. I then collected data of localization accuracy with an EKF versus without an EKF to show that EKFs will help improve localization accuracy. First, I'll talk about what the extended Kalman filter even is. Then I'll give an overview of the simulation and the robot in the simulation. And then after that, I'll talk about how my experiment was done. And then I'll show you and analyze my data. And finally, I'll talk about next steps. Let's first build some intuition about what an EKF even is. Let's say you're in your kitchen looking for a snack, but then suddenly the power goes out. You want to get back to your room, but how will you do that in the pitch black lighting? The most important thing is to know where you currently are. There's many ways you can do this. For example, based on how many steps you're walking in each direction, you can sort of predict or guess where you are. Also, when you touch something like a table, you know with pretty high confidence where you are, which is kind of like a sensor measurement. And by combining your footstep prediction of where you are with your touch prediction of where you are, you can create a more accurate estimation of where you actually are. And this is basically what the EKF does. But before diving more into how the EKF actually works, we first need to talk about the assumptions behind an EKF. In the EKF, all random noise is Gaussian, meaning it follows a normal distribution, and random noise also has a mean of 0. The true state model is assumed to be equal to the physics state model with added noise to it. And the measurement is assumed to be the true state with added noise. And this means that the physics model is essentially the mean of the true state, which is the mean of the measurement. In the EKF, the latest belief of the state is called the estimated state. And it also has an uncertainty variance attached to it, which is called state covariance. And the EKF works in 3 steps. First, the true state is measured with sensors, which is kind of like touching a table. Then, based on your previous estimated position, the next state is predicted using a physics model, which is kind of like counting footsteps. The measurement and the state covariance are also predicted. Using the uncertainty variance of the prediction and the uncertainty variance of the measurement, the Kalman gain is computed, which determines how much the measurement should be trusted. And the larger the K value, and K is the Kalman gain, the more trusted the measurement. Finally, the EKF uses the Kalman gain to perform a weighted average between the prediction and the measurement to obtain the most optimal state estimate. Here's an image showing a visualization of the EKF. As you can see, since the measurement has a lower variance, the estimate is weighted more towards it. Now that you know how the EKF actually works, I'll explain the details of my simulated robot and how I implemented the EKF. The robot in my simulation is a 4-wheel Mechnum drive robot with 3 odometry pods and a camera on top. A Mechnum wheel has small rollers attached to it at a 45-degree angle, which lets the robot move sideways when 2 wheels counteract each other. Odometry pods are wheels that can measure how far they've spun, and the camera can be used to detect images. In my code, I set the robot's state to include the X position, Y position, your angle, your body X velocity, and body velocity means the velocity in the robot's frame of view, your body Y velocity, and also your angular velocity. And velocities in body coordinates instead of global coordinates because body velocity tends to be less nonlinear. That means it can lead to more accurate estimates. For my localization types, I first have odometry, which uses odometry pods, which I mentioned earlier, to measure velocity. And if you want to find the position, you have to add up the velocities over time. But an issue with odometry is that slight error in velocity over time can accumulate to big error in position. You can also predict the state using a physics model, which uses Mechnum wheel mechanics to convert the 4-wheel motor powers into robot velocity. But this has the same error accumulation issues as odometry. A third method of localization is using camera measurements to detect image landmarks to find your absolute position. This allows for absolute position readings, but they won't be available all the time, which is one of the drawbacks. But using an extended Kalman filter, you can fuse together these three localization sources to allow for better state estimation. To do this, I set the physics model as the prediction in the Kalman filter, and odometry and the camera measurements are set as the measurements in the Kalman filter. In order to test how accurate the Kalman filter is, I need like an accuracy metric, and I used RMSE, which stands for root mean squared error. And to calculate RMSE, you find the error, which is the estimated state minus the true state. And the error included in the calculations is the error throughout all time steps in one simulation trial. And lower RMSE means higher accuracy. The 7 types of RMSE values that will be mentioned in this presentation are, first of all, XY RMSE, which is where the error is your translational distance error. Also, there's X RMSE, which is just your X position error. And then there's Y and an angle and all the other state components. Accuracy for all trials is tested on the same path, which is, I'll just call it the test path. And the test path works well for localization, testing localization, because it includes many unique types of movements the robot needs to follow. For example, there's straight lines, also there's left and right turns, and there's elliptical curves. And on the test path, I also put 2 image landmarks, which can be detected by the camera. There's 1 image landmark on the top and 1 on the bottom. To follow the path, I coded a pure pursuit algorithm, which is the path following algorithm that's relatively easy to implement and also does not require much computation power. First, I chose a few localization types to fuse together and created an EKF to fuse those sources. For example, if I want to fuse a physics model with odometry, I will set the prediction in the EKF to the physics model and the measurement in the EKF to odometry. And to test how accurate this localization method is, I will run 100 trials of the robot following this test path and then find the average RMSE values across all the trials. First, I tested velocity accuracy by disabling camera measurements, because camera measurements give you your position. The velocity RMSE values from using an EKF to fuse the physics model with odometry are lower than that of only odometry or only the physics model, meaning it's more accurate. The position RMSE with an EKF is higher because without using a camera, neither the prediction nor the measurement directly estimates position, and that can lead to less accurate position estimates. Next, I tested position accuracy by adding back camera landmark detection. Cameras help get rid of error accumulation because they measure absolute position, and this makes position accuracy much better. The following graph on the left shows how cameras can be used to correct your position, because the orange graph has no camera, which leads to error accumulation, but then the other one has a camera, so it corrects its position. But a bad thing about correcting position is that a big shift in your estimated position can lead to big jerks when path following. But overall, camera measurements still greatly decrease your RMSE, because on the table on the right, it shows how after you've fused a camera with the odometry and the model using a Kalman filter, it leads to much lower and more accurate estimates of your position. The EKF also has many drawbacks. For example, when used inappropriately, the EKF can lead to inaccurate localization. If DT, which is the update time, if DT is high, the linear approximations that are inside the EKF start to break down, and also odometry gets worse. And this leads to worse localization in general. The following graph shows how increasing your update time can lead to increasing RMSE, which is error. Another drawback to the EKF is if the system is highly nonlinear. Severe nonlinearity is an issue because many linear approximations are used in the EKF. We successfully applied a Kalman filter to fuse odometry, computer vision landmark detection, and a physics model. And the EKF definitely provides good results for the robot using the simulation, as quantified by the decrease in RMSE. It greatly increases localization accuracy while also not requiring much computation power. The next steps are to implement an EKF on an actual physical robot instead of a simulation. And on the physical robot, you would need a more realistic model that also includes acceleration in the state and takes into account for other factors such as friction and motor voltages. And a more advanced physics model can be obtained by training a machine learning model with human driving. Another state estimation algorithm to look into is called a particle filter, as it can perform state estimation on systems with non-Gaussian noise. Thanks for listening. Do you have any questions?
Awesome. Thank you so much for that presentation, Ethan. So for the audience members and also the other presenters, feel free to drop a question in the Q&A. I did actually have a question, Ethan, to sort of get us started here. And so what motivated you to use EKF over other methods?
Well, EKF it's like an industry standard level algorithm that many companies use for localization. For example, like in my robotics team, we visited like this company called Neuro, which is a self-driving car company, and they use the EKF, which I thought was cool because that means actual companies use it. And also an advantage of the EKF is that it doesn't require too much computation power, so it can run in real time on a robot, even if it doesn't have like very powerful hardware.
And are there other methodologies that you were considering? And can you sort of elaborate on maybe one or two of the other methods that are out there?
Well, one of them is using like a low pass filter, and that's like a way of reducing noise, but it isn't as effective as a Kalman filter in producing a more accurate estimate. And there's also other types of state estimation algorithms, such as the particle filter, which I mentioned, but that one's like pretty complex. So I wanted to start off with the EKF because that's like, it's a good starting point, I think.
Great. And just out of curiosity, what coding languages did you have to know ahead of time to do this project? Or did you have to learn a new coding language as you were going through the project?
Well, initially, like before I started the project, I was more fluent in Java, but an issue was like this EKF uses many matrix multiplications. So writing it in Java would be extremely painful. So then my mentor recommended me to use Python. So then I wasn't very good at Python, but I was able to learn about it. And then he taught me how to use NumPy, which is a library that lets you do matrix multiplication very easily and matrix operations. So I just ended up using Python to code my simulation.
That's great. How did you learn Python? Was there like a class that you were taking, or how did you sort of work through that gap in knowledge?
Well, before starting, I already knew some Python, like the basics, like for loop and like if statements and stuff, like the general knowledge. It was just from randomly learning about it over the years. I never focused a lot on Python, but then at Polygence, I started focusing a lot. My mentor mostly taught me a lot about NumPy, which was very helpful. And I think I learned a lot from him.
That's great. Awesome. Thank you so much, Ethan. I'll leave it for another 10 seconds here. If anybody has any questions about Ethan's project, feel free to drop that in the Q&A chat there. I actually did one last question, Ethan. What got you interested in sort of robotics and this field?
Well, I think I like robotics, especially software, because like it's kind of cool to just have math. Like you create some math, and that's able to make the robot do such like crazy things. And yeah, I think it's pretty cool. Like for the Kalman filter, you use like statistics and some calculus, and that's able to just fuse together various like types of data to make a very accurate estimate, which I thought was very fascinating.